Hello guys, nice to see you. How are you doing?
Good morning.
Hi,
Good afternoon.
good afternoon.
Good afternoon.
Hello. The summer is over, or it will still be warm. Hello everyone. Okay, so first comment that you can double check on Askar's YouTube channel. There are uploaded videos with instructions for like solving problems which were assigned for your homework last week. So most of like the most interesting problems are solved there. So you are welcome to go to his YouTube channel and double check if you have any questions related with that. And we here can continue further with consideration of kinetic potential energy. Just short reminder of previous lecture, we discussed in details the mechanical work, introduce the work itself, the concept of work done by a force, like constant force, also variable force in one and multi dimensions. And I've considered some example with the spring and attached body, how we can calculate work done by spring force, which is a function of position. So today we will continue with kinetic energy and go further. So if you have any questions, also you're welcome. Also can interrupt me on the way if you don't understand something. So I believe that most of people are already here and we can change the screen. Yes, you're right. The midterm will be this Saturday. I will soon send you an email with additional information on the midterm. But yes, it's coming. It will be on 11th September, this Saturday. So it will be done via long kappa. There will be some designated time interval within which you need to log, do this task and submit your answers. Another recommendation, please log in a bit earlier, maybe 20 minutes before the starting point of exam, in order to avoid situation when everyone logins at the same moment. And since there are many students this year, it could be that we have some issues, technical issues in that case. So just to be on the safe side, log in a bit earlier. Okay, and as I said, today or tomorrow, I will send you an email with some like reminder of the midterm and some information on it. Okay, so let us consider now one of forms of energy, which is kinetic energy. So let's consider some body with a mass m, which moves with some velocity with some initial velocity v. Let's call it v1. And we apply some force F to this body. So it moves under the impact of this force some distance delta x, and obviously it will be moving with some acceleration. Let's say since force is constant, acceleration will also be constant. So we can write A is equal to F divided by M. So there will be change in velocity. Here will be some V2. Maybe you remember, maybe not, we can recall this. During our first discussions, we derived kinematic equations. It was like position is equal to our initial position x naught plus v initial velocity v naught times t plus constant acceleration times t squared divided by 2. And also we could write for velocity that it's initial velocity plus a times t. So this is valid for one-dimensional motion with constant acceleration. And we also wrote another equation, which, so we expressed t from second equation and substituted here, as you remember maybe. And we had v squared is equal to v naught squared plus 2 times a times x minus x naught. So now we will use this equation and we can write for v2 for final velocity, v2 square is equal to v1 square plus 2 times a times delta x, like displacement. Now let us substitute instead of a its expression as a constant force divided by mass, and maybe let's write down so it will be more clear. Plus 2 times F divided by M times delta X. Now we need to do some rearrangement. We will put this V1 in the left side, then we will multiply left side by M and divide by 2. So we will get V2 square times M divided by 2 minus M V1 square divided by 2, and this is equal to F times delta X. And from our previous discussion yesterday, we know that this is nothing else as mechanical work W. So now here we can denote this as K1, sorry, K2, and this is K1. And what do we get? We get K2 minus K1, which is equal to delta K, and this is equal to omega. So this equation actually gives us this work, defines work kinetic energy theorem. So it tells us that if there is some work done by external force on the body, and the only change in the conditions is change in velocity of this body, then change that this work done by external force results in the change of kinetic energy. So that is important statement. We know that if we do some work on the body, some mechanical work, then if nothing else is changing, only velocity, then we know for sure that this work results in the change of kinetic energy. And kinetic energy is defined by the mass. So in general, kinetic energy is mass times velocity squared divided by 2. So that is the form of energy which any moving object possesses. However, it's definitely not the only form of energy. And in order to see the whole picture, we need to consider also others. So let us go and to the next slide and consider potential energy. So potential energy we will introduce based on the following example. So let us have some axis y and some ground level. So here is the origin, 0. Let's consider some body with a mass m. So there is some weight mg residing on this ground level. So its initial velocity, v initial, is equal to 0. Then we apply some force, which let's say equal to the weight, and move this body to some height. So its new position will be defined by coordinate h. And here it stays in stationary condition. So it's also v final is equal to 0. So we see that some work is done definitely by external force. Velocity didn't change, and means that there is no change in kinetic energy. However, the condition of the system changed because we had it at ground level, now it's at height h. So this work done by force F is actually transformed in some form of energy, which is not kinetic energy, and that is potential energy. So let us consider then the work done by this external force, which will be equal to F times integral from 0 to h, F times d, so sorry, it's not x. In this case, we have x is y, so it will be dy. So this force will be, it's defined by the weight of the body. So it will be 0 h, like in opposite direction to the weight of the body. It will be mg dy. And after integration, we get mgy from 0 to h. So then we get mgh, which is our potential energy as a function of position y. And position y is defined by this coordinate h. So we see that we have a conversion like of this work done by external force F is our gain potential energy of the system. So now let's continue this experiment. And once we already have this body at the height h, let it fall down on the ground level. So in this case, we will have the following. So initial velocity will be equal to 0, and final velocity will not be equal to 0. So that means that we have a conversion of potential to kinetic energy, because there are this external force is not acting anymore on the body. It is freely falling on the towards the ground level, and we can write that delta U, which is change in potential energy, is equal to delta K, change in the kinetic energy. And we can write mgh in this case. This is our potential energy, is equal to mv squared. We will put final here, divided by 2. So m and m we cancel out, and from here we can get final velocity, which is equal to square root of 2 times gh. So we see that initially we perform some, this force F, not we, perform some work and accumulated potential energy in the system. Then this potential energy can be converted into kinetic. So in total, we can write that kinetic energy plus potential energy in this example is constant. However, it's not always the case that we don't have any dissipation of energy. And most common example for dissipating energy is friction force. So because of friction, the surfaces which are in contact, they start to warm up. And that means that kinetic energy, for instance, converts into some other form of energy, which is not potential energy. So let us consider on the next slide so-called internal energy, some example. So let's say we have some flat horizontal surface and some body on this surface. So let's assume that it has some mass m, and it has some velocity v initial. So it moves on the surface, and there is some friction between some kinetic friction coefficient mu k between the body and the surface. So then it arrives at some new position on the surface. Keep in mind that this is horizontal surface, so means that the height doesn't change. Is it potential energy for falling object negative? There is some question. I mean, if we come back to this slide, then the work done by gravity force, which is conservative for so-called conservative force, when we pull up this body from ground level up, is equal to negative change of potential energy. So potential energy, when we consider the work done by the external force, what we did here, then it gives us potential energy. If we consider work done by gravity force, which is in opposite direction, obviously, then we will get here minus, and it will be minus potential energy. And later we will consider in more details that any work done by conservative force in a closed system, which is object Earth or spring mass attached to this spring, will be a result in negative change in potential energy. But that we will come to this point a bit later. So keep in mind that here we have horizontal surface, means no change in potential energy. However, while moving on this surface, final velocity is equal to 0. So it just stopped. And that happened because of conversion of kinetic energy, which we had initially, to some other form of energy, not potential, but so-called internal energy. We call it EI, internal energy. And that is, or we can put internal to make it more clear. So we have conversion of kinetic to internal. Internal means that we just heat up the surfaces of these two objects which are in contact and just increase this thermal energy. However, kinetic energy is lost because it's gone, it can be called as dissipated. So dissipated energy, because kinetic energy, instead of converting to some potential energy, which again can be converted in subsequently can be converted in kinetic energy, is dissipated in form of heat, and we just lost it because then we cannot use that heat to other to convert it in other forms of energy. So now let's say we can consider some example. Let's say we have some inclined plane. So here we have height h and some object here with mass m. So we let it go down without any friction. So here at the bottom, if we don't have any friction, we will have fully converted potential energy into kinetic. So it will be, can be written that mgh will be equal to mv squared divided by 2. So here will be some v velocity vector. However, if we have some friction, for instance, we have this body and there is some kinetic friction force acting on this, kinetic friction force acting on this body, then eventually we will need to take into account the conversion, like dissipation of potential energy towards this heating of the surface which are in contact. And in that case, we can write that will be mgh equal to mv let's say 1 square divided by 2, this velocity will be smaller than this. V1 will be smaller than V, because part of this energy, which is accumulated in the form of potential energy, will be gone to internal energy. So this should be taken into account, and this internal energy, we can write that it's equal to kinetic friction force times L, which is the length of this inclined plane, L. Obviously we need to take this into account, because this will be changing the final conditions which this system will reach. Okay. So now we know what like work done by the force, mechanical work, and concept of kinetic energy, concept of potential energy, and internal energy. That's good. Another thing which we need to consider is we need to differentiate between different types of forces. So conservative and non-conservative forces. So let us start with a conservative force. So let us consider such system of coordinates x and y, and we have some points A and B. A, B. So there are different options how we can go from point A to point B. Let's say we can go like this. We can go like this. And the path will be different. However, the displacement is the same. So in this case, the definition of, let's call it path 1 and path 2. In this case, if we have conservative force, this work done by going from point A to B via path 1 should be equal to work done by going via path 2. And what is also very important, if we have like full circle, if we come back to initial point A, we go to point B and come back to point A, then for conservative force, this integral along a closed loop, so it's marked as integral with this circle, for scalar product of force and conservative force and displacement vector should be equal to 0. So these are the conditions which a conservative force should follow in order to be called conservative force. And now let us consider some example of a conservative force, which is like the most common one is the gravity force. So we have again x and y system of coordinate, and here we have a body which is at initial coordinate y1. There is some mass of this body, m, and here is some final point where this body is moved with coordinate y2. So it can go like this with straight and go like this, trajectory. However, it doesn't matter because we consider the displacement vector, and displacement vector is this one along axis y. So for both cases, it just passes longer, but displacement vector defines how this work will be done. So we can write for gravity force that the work is done by minus mg. It's our weight. It's here, mg. And it goes to the opposite direction as axis y. So we have minus here times j unit vector times displacement vector. And displacement vector we can write as y2 minus y1. It doesn't matter here with which trajectory it goes. Matters only the difference between final, this interval between final and initial points times j. And that will be equal to mg times y2 minus y1. So if now we substitute instead of, oh, sorry, here's minus also. Minus, so we can write minus mg y1 minus y2. But here we don't need minus. So we just change it in the parentheses, taking into account this minus here. So now, if we consider situation when we come back to initial point, which is y1, instead of y2, we need to substitute y1. So when y2 is equal to y1, we get that work done by this gravity force in a closed cycle when we moved from point 1 to 2 and then back to 1, it will be equal to 0. So we see that both conditions for definition of conservative forces are satisfied. And we can claim that gravity force is a conservative force. So let us consider an example of non-conservative force. And as you may already know, we mentioned about this, what do you think the best example of non-conservative force? Any ideas?
Friction force.
Friction force, yes, it's dissipation of energy because of friction force. And let us consider this example. So again, we have some horizontal surface, our object on this surface, then it moves like this to a new position with path 1, and let's say with some path 2. So now what matters? Not displacement, but the path, so the length of the trajectory, because we know that work done by friction force, like kinetic friction force, will be equal to the product of the path. Let's call it S1, will be W1 work done by friction while moving this object along trajectory 1. And here will be Fk. It will be the same friction force, but the path will be longer here will be omega 2. And we can write that omega 2 obviously will be larger than omega 1. So that already tells us that this is not conservative force, because these works should not be dependent on the trajectory. It should be the same. Let us also consider option that we push this body back to its initial position. And you will see here that this will be, let's call it some pass 3. Some work will be done by friction force, while this body is moving back to its original position. Will be kinetic friction force times S3, and this will be W3, and then means that if we move around in 2 steps this body and put it back to initial position, then it will be V. Let's say we go with pass 2 and then come back with pass 3, and it will be V2 plus V3 is equal not 0, and that also not in line with the requirement for conservative force. So we definitely see that friction is not a conservative force. It's a good example of non-conservative force. So now we also need to mention this fact about internal force, internal conservative force in the system Earth body or spring body. Work done by internal conservative force when we move from initial position to some final position as f as a function of x dx. So this f as a function of x is internal conservative force. This will be equal to minus delta U. So negative work done by internal conservative force is negative, defines as the change in potential energy with the sign minus. So we can write that delta U is equal to U final minus U initial. That is equal to minus integral from x initial to x final f x dx. So from here we can get another, like a bit rearrange this. If we take derivative differential now in order to get rid of the integral, so we can write du is equal to fx times dx, and here we have minus. So from here we can define also force, internal conservative force, f as a function of x will be equal to negative first derivative of potential energy over displacement position x. So f is equal minus du over dx. So this is in one-dimensional case, and we can also define it in like three-dimensional case, multi-dimensional case. So this internal conservative force can be represented as minus du over dx times I unit vector minus du over dy times j unit vector and minus du over dz times k unit vector. And that is represented by one symbol, which is called gradient of scalar function u, which is function of x, y, and z. And of course, here we have minus. So with this, we gave the definition of conservative, non-conservative forces, and highlighted that any work done by internal conservative force in the closed system, Earth body or spring body, will be equal to minus change of the potential energy, which is minus delta U. Okay, now I think we have some time. We could maybe consider some example. Let's try to do it. Then we will continue with examples during Friday. But now we still have some time. Let's say we have a body on the surface with some mass mg. Here is reaction of the surface, and we have some force F and some kinetic friction force Fk. So now let's say we move this body along axis X in a new position. And this new position is located from the initial position at the distance delta x. So the question will be, what will be the velocity of this body in this new position? So, of course, obviously, by implying this concept of conservation of energy. So we can write, so we are interested in velocity. So we should definitely deal with kinetic energy. And let's assume here that V naught is equal to 0, initial velocity. So we can write that kinetic energy at the final position will be equal to kinetic energy at initial position plus work done by this force F minus work done by kinetic friction force. And we write here mv squared divided by 2. So it's equal to mv naught squared divided by 2, which is equal to 0. Then plus some positive work done by force F will be F times delta X, and minus, we have negative work done by friction, kinetic friction force, mu K times mg, which is reaction, and times delta X. So from here, we can get V square is equal to 2 divided by m delta x times F minus mu k times mg. So this is after rearrangement, and obviously final velocity will be 2 over m, the square root of this expression, F minus mu k mg. So this is how we will get based on the concept of conservation of energy. So here, as you see, we don't consider loss of motion. We don't consider some kinetic equations to calculate the velocity in new position, but based on the concept of conservation of energy between kinetic energy, internal energy, which is work done by the friction force, and also work done by external force, we can calculate velocity in a quite simple way. So we will make this example a bit more interesting for our next step. That in that case, force will be aligned at some angle, and the question will be how what will be the requirement for angle between force and horizon to get the maximum possible velocity after this displacement. So that is a bit more interesting case, but we will consider that in details already during our next discussion on Friday, because today we already are running out of time. Okay, guys. Thank you very much for attention. If you have any questions, you're welcome.
No, we don't have questions. Thank you. Goodbye.
Okay. Thank
Goodbye.
you for your attention.
Thank you.
Thank you, guys.
Bye.
Thank you. Goodbye.
Yes, sure. Calculators will be allowed.
Thank you. Goodbye.
You can use any textbook, and that's not limited. You can,
Thank you.
yeah, use all instruments, but instead of option, help from friend. That's not.
Can I ask the last question?
Yes, sure.
Do we need any like programs for recording ourselves during the exams, or it's not required?
No, it's not required. As I mentioned before, we trust you by definition. So hopefully that will be, our trust will be supported by your activity.
Okay,
Well,
thank you very much. Goodbye.
Midterms.
Thank you.
Good.
Good answers. Goodbye.
Bye.
Have a good day. Take care.
Goodbye. Thank you.
Bye-bye.
Goodbye.
Thank you.